about them, but qualitatively this is what happens. If, on the other hand, you take a semiconductor like silicon, and instead of putting phosphorus in that adds an electron, you put in a boron that removes an electron, because boron only comes with 3 electrons, not 4. Now every site where there's a silicon, instead where there's a boron, you've sucked an electron out of the lattice. It would be equivalent to having all the seats filled and having one empty seat by somebody leaving. And then if you all want to move a human from the front to the back, you have to shift to create the vacancy like the puzzle game, where the empty seat moves. Really, humans are still moving, but it looks to the observer like it's an empty seat moving. It looks like a bubble is moving from front to back. And so that's called the positive type doping. Now, because we pulled electrons out of where they were before, the halfway point is down toward where they mostly were instead of up toward where we added them. And this is called p-type. The Fermi level is statistically, thermodynamically, the same thing as the electrochemical potential of a material. At equilibrium, a material that contacts another material, they equilibrate until there's only one Fermi level. By definition, because otherwise they're out of equilibrium if they have 2 different Fermi levels by definition. Okay? So now what happens? Let's suppose we take that semiconductor, and in this example, we'll make it n-type, but it could be p-type. And we're going to do that because we want to raise that Fermi level up to add electrons to the solid to make it more conductive and to give us a driving force to do something with that extra set of charge carriers. Now, in most solar cells, you actually don't contact it with a metal. You would contact that absorber with another material of the opposite carrier type. If this was n-type silicon, you would put p-type silicon on the front. The physics is the same. It's just easier to explain if I put a metal there. Okay? But you need this asymmetry in order to establish left from right. So now we're going to see how that happens. This metal has its own Fermi level. That's the orbitals at which the metal, like a piece of gold, have all its orbitals occupied and then empty above that. And it might be there. And we dope the silicon to make it there. Now if I take that doped piece of silicon and that metal and I put them together, I touch them, or I evaporate them, or I contact them, they are not in equilibrium anymore, because by definition this Fermi level is different than that Fermi level. And so they won't stay that way. They will move their Fermi levels until they are equal everywhere in the system. That happens very quickly with 2 conductors. In fact, in a microsecond or less. And